Hello everyone, I'm Yang Shi from National University of Defense Technology. The title of our paper is Towards High Efficiency Data Centers via Job-Aware Network Scheduling. Today, we will introduce our work in these 5 parts. First is the motivation part. It has become universal for users to deploy their jobs into data centers in order to satisfy the requirements for various resources and performance, such as the needs for computational resources, economic considerations, or reliable reasons. As a result, these jobs will face resource competition within the data center. The job completion time, which is JCT, increases and the efficiency of the entire data center stays low. Among various resources, network bandwidth is critical to the performance of distributed jobs. It has been reported that as much as 50% of the time taken to complete a job is spent transferring data across the networks. So, a good network scheduler is needed. A large number of network scheduling techniques have been proposed over the past decade. Traditional flow-oriented scheduling algorithms generally focus on reducing flow completion time or improving per-flow fairness. However, the unawareness of the detailed jobs makes them not efficient. In light of this weakness, the core-flow abstraction is proposed as a major leap forward for job-aware network scheduling. A core flow is defined as a collection of all flows between two consecutive stages in a distributed job. However, the complex interactions between communication and computation in complicated modern jobs have made core flow insufficient to support jobs requirements. In many popular deep learning frameworks, a job is represented as a DAG. During their processing, network transfers are consumed based on the dependencies in the underlying DAG. Thus, in these jobs, not all flows within a core flow are equivalent from a job's perspective. To demonstrate this complex interaction, we conduct an in-depth investigation of network transfers within the TensorFlow. The results are plotted in this figure. The yellow and red lines denote the time steps of the receiving and consuming of transfers, respectively. It is evident that a large time gap exists between these two lines, which indicates that even after the data transfer is finished, subsequent computations will still need to wait a while before beginning. It should be also noted that a data center typically contains plenty of various jobs. Therefore, it is not easy and realistic to obtain the DAG of each job, such as those running a Spark, an audio or video service, or a file transmitting job. Bearing the above points in mind, we consider the following question. Taking advantages of the internal network requirements of different jobs, can we build a job-aware network scheduler that reduces the JCT and improves the efficiency of the entire data center? To address this problem, we propose JIT, which is short for just-in-time, a network scheduler designed to improve the performance of the jobs according to their DAGs. Meanwhile, for those jobs that do not provide DAGs, JIT has only a minimal effect on their performance, thus improve the efficiency of the data centers. Now, we will introduce the proposed latest arrival time based on previous observation. As we demonstrated before, even the network transfer finishes, it still needs to wait a while to start the subsequent task. Here we use a toy example to show why this data waiting exists. Assume both transfer tasks T1 and T2 are transmitted at time 0. Then C1 and starts immediately. However, C2 cannot start due to the dependency on C1. Therefore, T2 had to wait for C1's completion to be consumed by C2. This will cause the time gap. So, we define the latest arrival time, LAT, which is the latest time that a network transfer can arrive without delaying the subsequent computation. We also devise a heuristic to estimate the LAT on the basis of calculating the finish time of a call flow, as shown in the right. This algorithm considers both computation and communication at the same time. The most important step is in line 13. The LAT of a transfer is defined by three parts: the LAT of its parent transfers, the time needed to go through the corresponding DAG, and the transmission time of this transfer. We also provide an example of LAT calculation. The detailed steps are stated in our paper. Please refer to it for better understanding. Next, we will illustrate how we build the scheduling model with LAT and solve it. Firstly, we build an integer linear programming model with according to our scheduling objectives. The objective is intended to minimize the maximum bandwidth usage among all links in all time slots. This objective avoids the situation in which the scheduled jobs occupy all the network resources, resulting in more bandwidth being available earlier to accelerate unscheduled jobs. To achieve this objective, there are four constraints that must be satisfied. Equations 4 and 5 indicate that the total bandwidth usage on all egress and ingress links cannot exceed the bandwidth limit C. Moreover, equation 6 implies that all data in transfer should be transmitted between the start time and LAT of this transfer. The final constraint, equation 7, works to limit the transfer so that it can only be transmitted between its begin time and LAT. The original ILP model is difficult to solve, owing to its being NP-hard, but fortunately, a special class of LP can be transformed into an equivalent LP so long as two conditions are met, namely a separable convex objective function and a totally unimodular constraint matrix. If these two conditions are met, we can use lambda representation technique to transform an ILP model to a LP1. We have proved that our ILP model meets these conditions, and the details are presented in our paper. Here we omit it. This is the final LP model used in our JIT scheduler. Efficient LP solvers can be applied to solve this model. In our evaluation, the solver we use is Groby. Even we use an LP model to reduce the solving time, it still usually needs tens of seconds or more, which is unacceptable in real life. Accordingly, to make JIT most practical, we simplify it in two key respects based on our observations. Firstly, a subset of all network transfers is selected for consideration within the LP program. The formulation suggests that it is easy to infer that transfers with small LHs will be transferred with higher priority. Thus, we can treat the transfers with larger LHs as background traffic and send them using the remaining bandwidth. A parameter alpha is used to denote the fraction of chosen transfers, set to 0.4 in line with previous experience. Secondly, scheduler only reschedules when a network transfer arrives for a new job. We believe that this simplification is reasonable, as it has been observed throughout our profiling using TensorFlow that the start times of all transfers are almost equal. When these two mechanisms are combined, it is clear that JIT is more practical in real-life scenarios. Then, we present the evaluation results of JIT. We adopt 5 classic stack-based deep neural network training jobs, namely LNet, AlexNet, VGG16, Inception, and ResNet 152, as the workloads in our evaluation. Moreover, to verify JIT's ability to improve efficiency within a data center network, we also deploy some file transfer jobs within the cluster with person request arrivals. We compare 3 network scheduling schedulers with JIT in our experiments: original TensorFlow, a call flow scheduler Synchronia, and TicTac, which is a single job scheduler based on DAG. We plot the JCT of evaluated jobs in this figure. As we can see from the figure, all 5 of the evaluated jobs have been significantly accelerated using JIT. In general, JIT achieves an average speed up of 1.55 for the 5 tested jobs. The differences between speedups of different jobs are due to the differences in average waiting time of transfers within each job, which we can see in the middle figure. These jobs with a longer waiting time, like Inception and VGG16, then show a better acceleration with JIT. To examine the results in more depth, we also plot the waiting time of each transfer in Inception in the right figure, which when compared with the original results in TensorFlow, it is obvious that the gap between the receiving and the using time of transfers has been narrowed. This means that transfers are quickly consumed by subsequent computation following transmission, resulting in less network waste than that generated by the original TensorFlow. Another metric in our evaluations is the bandwidth remaining after specific jobs are scheduled by JIT. Thus, we plot the CDF of the remaining bandwidth for 4 schedulers. 2 observations can be made. Firstly, the minimum ratio of remaining bandwidth is increased. Secondly, the remaining bandwidth of JIT is more balanced than that of comparison schedulers, mainly between the section from 33.4% and 79.3%. More directly, we examine the JCT of file transfer jobs to check the global efficiency. Here, we take the JCT of these jobs in an empty data center as a baseline and compare the increases in JCT with different schedulers. These These results confirm that JIT is able to minimize the effect on unconsidered jobs and hence make the entire data center network more efficient. As noted above, we go on to optimize the solving speed of JIT by choosing a subset of transfers. Here, we discuss how the value of alpha can affect JIT's performance. The value set of alpha is from 0.1 to 0.6. As alpha increases from 0.1 to 0.6, it is clear that the accelerating performance improves from 1.09 to 1.62. Meanwhile, the remaining bandwidth reduces from 48.2% to 32.4%. Hence, we adopt this figure to we adopt the alpha we adopt the value of 0.4 to balance the performance and efficiency of JIT. Practically was a primary concern when designing JIT, which means that JIT needs to be efficient in terms of runtime. Therefore, we recorded the time taken to solve the LP problem. From this figure, we can see that the linear program is rather efficient. It takes about 0.4 seconds to solve a problem with about 40 jobs. Even when the number of jobs increases to 70, the solving time is still less than 1 second, which is acceptable in real-life situations. In the last part, we will present some ideas about future work briefly. First, we plan to design a global network scheduler that considers all jobs together. Secondly, we want to devise other scheduling algorithms based on LAT, such as priority-based heuristics. These simple heuristics may be implemented inside programmable switches to improve the scheduling efficiency, which can also improve the efficiency of the data center network. That's all of our presentation. Thank you.